Yo! How's it going, everybody? Welcome back into the stream. I hope you're having a wonderful day so far. Your boy's name is Michael, and we are back. Hey, how's it going, Danny? Welcome in. Appreciate you for joining me here. Welcome, welcome, welcome. What are you doing? What's going on? All right, everybody. So today we're going to be working on problem set 3 of MIT 6.0002. Let me turn off the music here. Or at least turn it down here. All right, so today we're going to be working on MIT 6.00. Chill. All right. Today we're going to be working or jumping back into MIT 6.0002, which is Introduction to Computational Thinking and Data Science. It is a great course. It's kind of getting ourselves kind of thinking more of like a statistical-based programmer and getting kind of a head start and lead into machine learning. And then we're going to hopefully be diving into some more heavy machine learning courses after this. Yeah, so we are on week 8 of the lectures, and that brings us up to problem set 3. So we are going to be taking a stab at this, and I'm going to probably code for I did I did a late night session of programming last night, and I'm definitely feeling it today. So I'm probably only going to code for about maybe an hour maximum, probably an hour and a half today. So we can probably finish the first couple chunks of this, and then we'll have a part two to probably wrap it up, and potentially a part three if we have to, because this one does look pretty long. It's a 14-page PDF. Oh, jeez Louise. Hey man, how's it going? Um, on Cat, hey man, what's up too? If I'm not wrong, weren't you doing DSA 2, bro? You're already like 9 years late from the due date. No! No! Ah! My dog ate my homework! Ah! Ah! No. Uh, yeah, that's funny. Yeah, so we are a little bit late here. But as some might say, better late than never. Let's jump into problem set 3 here. Bro, do you have any tips for learning chemistry? I'm really bad at it. It's O levels. O levels. Let me get a quick refresher here. O levels. Let me refresh my memory. Like oxygen, ordinary levels. Chemistry. Oh, organic chemistry stuff. Bruh. Organic chemistry. What, are you talking about organic chemistry? What do you mean O levels? All levels? I started DSA like 3 days ago. My brain is already cooked. No worries, dude. Let's learn it together here. We've been reading You can go check back our read along of Introduction to Data Structures and Algorithms in Python. We've read up to chapter 11 in that book, and it's a great read to kind of get you kind of going, and so you could kind of read it with me alongside, and maybe that could help out a little bit. But I'm also reading Introduction to Algorithms by CLRS, which is kind of like the holy Bible of algorithm books. So that's why I wanted to get that one out. Tomorrow, be on the lookout for tomorrow. I will be uploading the audio book. It's chopped up. It's 25 minutes long. It's the entire chapter 1 of me reading it aloud. Read aloud, study along. It's really nice, and it should be fun. It should be good if you guys want to get that book and listen to it. Okay, let's go ahead and get into today's problem set. Oh, definitely, probably. C++. I mean, it's just kind of a lot of pseudocode, honestly. It's not even a lot of Python code. There is Python code for sure, but the topics are still there. Introduction to Algorithms, you can definitely read along with us because that one is pretty universal. What? I don't want to go 140. Okay, here we go. Introduction. In this problem set, you'll design a simulation and implement a program that uses classes to simulate robot movement. We recommend testing your code incrementally to see if your code is not working as expected. To test your code, run the problem set 3 _test f16.py. As always, please do not change any function signatures. Read the style guide. Make sure you console the style, blah, blah, blah. Okay. Using Python's random module. You'll be using Python's random module, so check out its documentation. Make sure you import random at the top of the file. And some useful function calls include random.randint, which is a random integer, such as that the random integer is less than or equal to the inputs A and B, or greater than A, I'm sorry, it's in between these two, or them. Random.random returns n float, such as is between 0 and 1, and random.seed 0 starts the pseudo-random number generator. Python uses the same spot, so the sequence of random numbers it produces from the different runs of your code will be the same. So you may find that using this useful while debugging. Simulation overview. iRobot is a company started by MIT alumni and faculty. Funny enough, I got an iRobot Roomba that I run pretty much every day. Um, right? Roomba robots move around the floor, cleaning the area they pass over. You will code a simulation to compare how much time a group of Roomba-like robots, will take to clean the floor of a room using two different strategies. The following simplified model of a single robot moving in a square 5x5 room should give you some intuition about the system we are simulating. A description and sample illustrations are below. Alright. Oh, hold on, my fire alarm's gonna go off. Sorry, I got some chicken nugs in the air fryer and they got a little smoky. Okay. The robot starts out at some random position in the room. Its direction is specified by the angle of motion measured in degrees clockwise from north. Okay, so north's up here, measured in degrees clockwise from north, right? So up north here, 180 degrees would be down south. Cool. Its position is specified from the lower left corner of the room, which is considered the origin 0.0. Its position is specified from the lower left corner of the room, which is considered its origin 0.0. The illustrations below show the robot's positions indicated by a black dot, as well as its direction indicated by the direction of the red arrowhead. Okay, time t sub 0. The robot starts at the position 2.1, 2.2 with an angle of 205 degrees. So 180, 200, 205. So it's going over this way, right? The robot has moved one unit to the direction it was facing, and it's now facing, now it's the position still facing the same way, right? The robot has moved one unit in the same direction, boom, and now it's here, cleaning another tile. The robot could not have moved another unit in the same direction without hitting the wall, so instead it turns to face in a new random direction, 287 degrees. The robot moves along until its new direction, along its new direction to the position 0.3, 0.7. So it finds it turns and finds a new random and goes, okay, I'm going over here. Okay. D, simulation concepts. Here are the concepts of the simulation model. Room. Rooms are rectangles divided into square tiles. At the start of the simulation, each tile is covered with some amount of dirt, which is the same across tiles. You will first implement the abstract class rectangular room in problem 1, and then you will implement the subclasses empty room and furnished room in problem 2. Robot. Multiple robots can exist in the room. iRobot has invested in technology that allows the robots to exist in the same position as another robot without causing a collision. Oh, cool. You will implement the abstract class robot in problem 1. You will implement the subclasses standard robot and faulty robot in problems 3 and 4. More details about the properties of these components will be described later in the problem set. Helper code. We have provided two additional files, the ps3 visualize.py and ps3 verify movement27.py. These Python files contain helper code for testing your code and for visualizing your robot simulations. Do not modify them. If one of these files throws an error, it's because of an error in your code implementation. To test your code, run the F16, right? So these just are helper code for this. Problem 1. Implementing the rectangular room and robot classes. So we'll probably tackle problem 1 today. I think that'd be probably a good goal for us because it's a chill night. Let me know how you guys are doing. Read ps3.py carefully before starting so that you understand the provided code and its capabilities. Remember to carefully read the doc strings for each function to understand what it should do and what it needs to return. The first task is to implement two abstract classes, a rectangular room class and a robot class. An abstract class will never be instantiated and instead is used as a template for another class. We learned that in data structures and algorithms in Python, right? I think it's in chapter 2 or maybe chapter 3 where we learned about abstract base classes or ABCs, where these just serve as template classes that are actually never instantiated on their own. They're served as adoptions or parent classes to children to then have the children serve actual functionality. That you can create multiple children across this template to access kind of a static template form, right? Rather than copying and pasting the same class multiple times, I guess. Yeah, it's just an optimization. Yeah. Abstract classes define methods that are shared by their subclasses, right? Their children. These methods can be implemented in the abstract classes, but they can also be left unimplemented and instead implemented in their subclasses. In the skeleton code provided, the abstract class contains some methods which would only be implemented in the subclasses, right? We only want to have some methods in the children so that we can have like distinct children, like let's say like boy, girl, child, just for purposes like that, right? You can infer methods then. These methods can be implemented as abstract and will also be left, okay, right? If the comment for the method says do not change, please do not change it. Your test code can go along by running the provided test in ps3 test f16.py. In ps3.py, we've provided skeletons for these classes, which you will fill in for problem 1. We've also provided for you a complete implementation of the class position. Alright, now we're going to implement the rectangular room here. And okay, gotcha. Let me grab my chicken nugs right quick. I'll be right back. I haven't had any dinner yet, so give me 1 minute. All right. Don't mind me, guys. I'm sorry. I'm hungry. Okay. Class descriptions. So hold on. We provided skeletons for these classes, which we've also provided a complete implementation of position. Class descriptions. Rectangular room represents the space to be cleaned and keeps track of which tiles have been cleaned. Robot represents the space to be cleaned and keeps track of which tiles have been cleaned. Okay. Robot stores the position, direction, and cleaning capacity of a robot. Position represents a location in x and y coordinates. X and y are floats, satisfying this condition where it's less than the width and less than the height, the maximum height. Okay. Here we go. New chat. All right, here we go. Mouse watering over here, guys. Okay, so we're gonna work in ps3.py. Okay. Oh, we don't have PyLab here. How do we do this? Python -m venv. Is that how you do it? Should I do .env, venv? What's the is venv or .venv typical? So we'll clear out of here. Okay, now we're in our virtual environment. Yeah. Now we'll go pip status. Oh, not pip. Pip upgrade pip -- upgrade. Oh. How do you do it? Pip, whatever. We'll just do pip install pylab. Pip install -- upgrade pip. Oh, okay. Not find a version that satisfies requirement pylab from versions none. Pip install pylab. Install matplotlib numpy. Okay. Pip install matplotlib and numpy. All right. Pylab. Cool. Let's add a file. That's how we do it. VNV/. Okay. So if I keep this here and then get rid of this, still is got rid of. So that takes care of it. Okay, cool. So let's do this. Let me go. Hold on, guys. Sorry. We want to do pip freeze. We'll write this to a file called requirements.txt. And then we'll go no. That's good. B&B plus big You guys can get access to this on my GitHub. You guys can see all the problem sets and my answers. Let's add in this pie cache. It'll probably happen too. Okay, let's get going here. Okay. Rectangular room implementation details. Representation. Rectangular room. No, sorry guys. Go back to it. You'll need to keep track of which parts of the floor have been cleaned by the robots. When a robot's location is anywhere inside a particular tile, we will consider the dirt in that tile to be reduced by some amount determined by the robot. We consider the tile to be clean when the amount of dirt on the tile is 0. We will refer to the tiles using ordered pairs of integers. Tiles can never have negative amount of dirt. Starting conditions. Initially, the entire floor is uniformly dirty. Each tile should start with an integer amount of dirt specified by dirt amount. Okay. So we're going to do rectangular room object here. A rectangular room represents a rectangular region containing clean or dirty tiles. A room has a width and a height that contains width times height tiles. Each tile has some fixed amount of dirt. The tile is considered clean only when the amount of dirt on this tile is 0. I'm gonna add in a testing.py. I'm going to from VS3 import rectangular room. I'm gonna do a room equals to a rectangular room, and then we'll just leave it at that for right now. And then we're going to print room. Something on my leg? What the heck? What was that? What was that? That was so bizarre. Keep getting distracted, man. Should have been done with this problem by now. Nuggets and now ghosts on my leg. We'll just see. We'll do that right now. Okay. Okay. So a room has a width and a height. It contains height times width tiles. Each tile has some fixed amount of dirt. The tiles only consume the amount of dirt is 0. So you have a width and a height and a dirt amount. Width is an integer, height is an integer, dirt amount is an integer. Easy. Self dot self dot width equals to width. Self dot height equals to height. Self dot dirt amount equals to dirt amount, right? Easy. So do we have to assume that these are integers? Do we have to do any checking on these? I don't know. Like, would it be... Like, should we... I don't know. Would it be dumb to implement our own function here? Def check int. I mean, they're all integers, so, but whatever. So raise the value there. But you want to raise this, what is not implemented error? What does it mean by this not implemented error thing? I've never actually really invented it from implemented yet. Can we delete this? I think. I mean, is it just a... I don't want to try to overkill this. Let's just... Right, set the variables. Okay. If width greater than or equal to 0. I guess you're supposed to comment it out or implement function or delete. Yeah, let's comment it out. Let's maybe not delete anything just for clarity's sake. But I feel like, I don't know, am I just being overkill because this class is like kind of easier Python? Maybe to some, like basic classes, like am I I don't know. I will see. Maybe like Maybe they have some checks in these testings that make you implement some checking or something, but I don't know. It's pretty bland here. Right? Cool. Width equals height. So it just has a height, width, height. So we have to say like what? Self.room? Do we have to give it like a variable self.room equals to an array of none type where we want how many columns do we want, which would be the width of the room, and the height of the room is the rows. So it would be right, none times width times oh, we can't do that. We have to say we have to do like this. Is that how you initialize a matrix just in one line like this? Can we do this? Where we use a list comprehension where we create a list object which is none by the width for every row in height. Right? So none for every column in width for every row in height, right? So, but we need to set amount. Oh, sorry, it's not none. I'm being dumb. Do we do dirt amount dirt amount, do we do it like this? Can you do dirt amount times width like this for row and range of height? Let's try that. Let's not go to GPT. Let's try stuff some the old-fashioned way here. Let's give a width equal to 5, height equal to 5, and a dirt amount equal to 1. And let's print room dot room. Oh, let's go. So we want a 5 by 5, so 5 rows. Now let's make sure we were doing this right. So We want to make sure the number of rows, which is the number of lists in our initial overarching array. The number of columns is the number of objects in each individual list, right? That's how I remember it. So the number of rows is each individual row is a list, which is, so let's make a little comment here. So width is going to be row columns, and height is going to be rows. So if we increase the number of rows by 1, we should get an additional list. And then let's print length room here. Good, 6. Perfect. Now if we print length of room index of 0, just one of the individual tiles, we should 5. Perfect. So we are setting up our matrix appropriately. Look at us. Print debuggen. Cool. I gotta show the AI. I gotta say it. Boom. Dude. Cool. Cook it, boys, cook it. Pause, gotta get my drink. Okay. So now we have a room. So I think that's what we're supposed to do, right, is create this room object. And this is a rectangular room. Perfect. Done. Boom. Starting conditions. Initially, the empty floor is uniformly dirty. The entire form is uniformly dirty. Each tile should start with an integer of dirt specified by dirt amount. Okay, whatever. Okay, so we do have some checks here though. Tiles can never have a negative amount of dirt. I want to write some like check functions to check to make sure that these are, I mean, I don't want to write them all in here and like reuse them. If width less than 0, or I mean, we could do this, height less than 0, or dirt amount less than 0, we're going to raise a value error saying we'll say rectangular room params greater than 0. All params must be greater than 0, whatever. Talk about MIT clean code, am I right? Interesting what they got going on here. Okay, next. Oh, crap, we got a bunch of functions here to write. Return true if the tile MN is cleaned. Assume that NN represents a valid integer, valid tile inside the room. Return true if MN is cleaned, otherwise false. This consider clean. Oh, okay. This is so easy. I'm just stalling because I'm eating my food here and I'm chilling. Not in any rush, but this is not really that challenging. So all we have to do is say return. We can just do one line. Return self.room index of m index of n equal to 0. Boom, done. Get num clean tiles. Returns an integer, the total number of tiles, clean tiles in the room. Now, this is easy too. Should we just do a loop, or is there a clever way we can do it, huh? Whatever, we'll just do it linearly. For tile, or no, for so for room has rows, so for row in self.room, and for column in self.room, sorry, in row, right, we're going to, for every column in that row, we're going to access the this is the list for every row. I don't want to do that. I want to say length. Let's do this. Length of rows equals to length of columns equals to length of rows. The number of rows is the actual length of the self.room, and the length of the columns is the length of self.room index of 0, if there is any, which there should be. Kind of wants us to assume stuff based on these notes, so I'm pretty sure MIT is kind of being a little lax here. So the length of columns is the actual length of the individual tiles in the row. And we say for I in length, or in length of rows, for, I'll say this is a row, and for J, or column in length columns, this will give us integer indexes. Now we can actually index into well, why am I even doing this? What am I doing, dude? Why don't I just go into each row, and then each tile in each row, and then check if that tile is less than or equal to 0? What am I doing, dude? This ain't leak code. This is MIT sophomore course. Chill, man. For row in self.room, right? And for every tile in the row, we're going to if tile less than 0, number of clean tiles. Okay, so if it's greater than 0, then we're going to increase our clean count. I have a problem. I always try to overcomplicate stuff. Leak code has me cursed. We'll just increase our clean count by 1 if the tile right? The room has rows, and then we have individual tiles in said rows. We're accessing the tile values and then seeing what the value is. Sorry, it's getting late, you guys. You know I'm starting to fog out here. It's getting foggy. For every row in the room, we're going to access every list. And then for every tile in that list, which is every number, if that tile is greater than 0, it's... Oh, it's not clean, sorry. If it is equal to 0, we have a clean tile. And then we're just going to return... Oh my gosh, clean. Right? Anybody have any slow? Do we have any slow? Probably wanting us to throw in some sort of algorithm to speed this up to n log n rather than linear. Or not linear, n log n, I mean just log n, sorry. What do we think? Pretty simple? I was overcomplicating it. All we need to do is just access each row, right? And then access each tile. Check. Check, check, check. Is position in the room. Determine if position is inside the room. A position is a position object. Returns true if position is in room, false otherwise. Oh crap, I forgot about this position. A position represents a location in a two-dimensional room where the coordinates are given by floats x and y. Okay, so you have some float values, and then you get new position, which does all that. Okay, so you just have to check if it's within the bounds of your area. Okay. As long as, sorry, where am I at here? Where am I at here? Oh my gosh, where am I at? Holy cow. Here we go. Wow, a long ways to go. So a position object. Okay, got you. It's more of a simulation type of problem. Like it's like, I don't know. Yeah, it uses some structure, like class structures, but more, I don't know. What do you guys think? Is it a DSA problem? Okay, so we have a position. So we want to say if position dot x, which is going to be the x direction, which is the amount of columns, or the width, right? Oh my gosh, I keep losing the spot, dude. Okay, if self.position dot x value is greater than if it's greater than our, if it's greater than the allowable width, which will be the number of columns. So self dot length, self dot, I'll just do self dot width. I have the width here, right? or position.x is less than 0, return false. If position.y is greater than our self.height, or the position.y itself is less than 0. Do we have negative position? No, this is origin 0, 0. Alright, yeah, and this is 1, 2. This is at 2.1, 2.2. Yes, perfect, okay. So, right. We're going to return false here. Else we're just going to return true that this is a valid position. So let's do some testing here on these really quick. So we have get number of clean tiles. So we have this rectangular room here. Let's say dirt amount equals 1. Let's go print room dot get num clean tiles. Zero. Perfect. Now if I go ahead and modify here, room dot room index of 0, so the first row, first column equals to 0, and then we run said function again, 1. Perfect. Alright, so that is test those guys. Now let's just do one more test really quickly actually. Let's make sure it goes up by a second call to the next one, so 2. Perfect. Nice. Okay, so we then are trying to test this function. So is position in room. So we're going to say from PS3 import position. Right. We're going to create a new position. X equals to, let's make it 0, 0. So it should be in the room, right? At the origin. So let's print room dot room dot, oh sorry, no, room dot is position in room, and we're going to give it the position variable. This should be true. Now if we change this, if we change this back to 5 by 5 and then change this to 5, this should still be true. False. Oh, come on, let's go. Let's test the height of this position now. Well, let's test negative on the room. False, perfect. 5.5. False. 5.0. True. Okay, let's test then here. -1 on the height. False. 5. True. And 6. This should be false. Perfect. Look at that, dude. We know what we're doing. Yo, Jesus, what's going on? We're doing MIT 60002 Introduction to Computational Thinking and Data Science right now. We're working on problem set 3, which is just either prior or after the week 8 lecture, depending on how you look at it. So before we can move on to week 9, we need to complete problem set 3. So we are completing this one over the next couple of days. For those that are new here, my name is Michael. I have a degree in human biology and a minor in chemistry. I work as a formulation chemist for a biotech company where I have been doing that since I graduated back in 2021. I I manufacture biological controls in very big bulk, and I've been teaching myself how to code after work every single day for a little over a year now. So thank you guys so much for being here. I'm pretty dedicated to learning code and teaching myself by doing courses, building projects, and the like. And I do that all live, 100% transparent on the stream here. So thanks so much for being here. And yes, welcome to the coding journal. All right, next function here. I'll do one more function, or maybe I'll just wrap up this class and then I'll probably call it a night there, and then come back tomorrow to tackle some more after work. Got to get on earlier tomorrow. I keep getting off of work and sitting on the couch and snoozing for a little bit. Return the amount of dirt on the tile MN. This is so easy, dude. Self.room, index of M, index of N. So this is row 1, tile 3, right? And so you go and you return that value. So rather than having to do this, so now we can say print room.get amount of dirt. M, we'll go 0, 0, 1, perfect. Now if I change this with this change here, 0, perfect. Okay. Next, get num tiles, returns the total number of tiles. Do not change, implement in subclass. Do not change, implement in subclass. Do not change, implement in subclass. Was I supposed to change this one? Yes. Okay. So this says these are do not change. So then subclass empty room. An empty room represents a rectangular room with no furniture. I don't want to jump to to another problem here, but this one's so easy. Just return length of 0, 0. Return the length of self dot room, or sorry, that's it, right? Just the area of the room. Right, if it's 5 width by 5 height, you have 25 tiles. That's pretty easy. Huh. Was I supposed to implement? I'm confused a little bit. Do not change implement in subclasses. Implement in subclasses. So I just worried that I don't want to change something on accident. So if we go to test F16 here and we run what is import imp? It's old. Import lib. Is that what it's called? Alright, I think that'll do it. Should we keep going here or be done? Maybe I'll be done at 10:30. So if we run this testing, no module load compiled. So I have this old style Python for loading a compiled Pike file, pyc. Deprecator is mentioned. You'll need to use import. This is import from util spec from file location module. I'm not really sure what to do here. Anybody know how to resolve this old issue? This is from problem set 3 of MIT 6.002 from 2016. Back then it was still evolving. Okay, let's just have it do it. I'm fine with having it do it for us here because I don't really know what it's doing. I kind of just want to create a module spec from the compiled file. So if we just take this and put it instead of here, import lib.util. Most of this file directory and users, repos, 6 triple. Oh, hold on. Check from file location, name, and location. So we want to do test.py, so let's do /problem set 3, and then we have to come back out of here, or we could just go here and go, sorry, test.pyc, get relative path, paste that here. Now if we run, bad magic number and test. Import error by 6. Channel logo is compiled with a different Python version than the one you're using now. Oh. Import the py files directly with import test or import. From test, import test. From test, import test. possible to import them directly, it said. So let's see if we can do that. Uh, Not sure. That sucks though. So we might just have to write our own tests. Make sure this works. Okay, so the class is a little bit old, you guys. It's our Python versions are out of whack, so they're not gonna work here. So we could downgrade potentially, but I don't really think it's super prevalent. As long as we kind of are getting the gist, we're not getting graded on the assignment. So as long as we're getting the gist of the information kind of correct and doing our own testing, I think that's sufficient in my opinion. I think you guys all probably would agree as well. As we're not getting credit for this course. We're not graduating from MIT. The real value of the course is, there's no degree, is the content. So as long as we're grasping that, that's what matters. Yes, it does suck. Can't officially like check it off with the tests, but I think MIT would understand. Hopefully. Okay, so that finishes the the abstract class of the room or rectangular room object, where we had to initialize a room, which is a 2 by 2 matrix with a height and width and a dirt amount within each cell of the height width. We then got some functions to determine if the tile is clean or not, and how many clean tiles there are in total, as well as if the position is in the room, for a position object being in the room. We also wrote for a get dirt amount, a simple one-liner. So these functions, they do, I will preface, they do have us assume that the inputs are correct. They don't have any, we're not having any checking or doing anything like that. So just keep that in mind. It is pretty kind of bare and not really that you know uh, protective of these inputs, but we are under those assumptions, I guess. And then these last three, get num tiles, is position valid, and get random position, are implemented in the subclasses of the rectangular room. So what's robot? Should we do the robot? Come on. Initialize a robot. Represents a robot computer cleaning a particular room. At all times, a robot is particular position and direction in the room. Also have a fixed speed and cleaning capacity. Subclasses of the robot should provide movement strategies by implementing update position and clean. Initialize a robot with a given speed and given cleaning capacity in the specified room. Okay, so self.room is equal to room, right? Self.speed is equal to speed, and self.capacity is equal to capacity. Initialize a robot with a given speed and given cleaning capacity in the specified room. The robot initially has a random direction and a random position in the room. We're not given any of those. Okay. I think is that all we need to do? A positive integer the amount of cleaned dirt or cleaned by the robot in a single step. Does it reset? How much is cleaned so far? Like 20% full, 30% full. Okay. Get robot position. Let me get where my tunes go. Returns a position object given the robot's position in the room. Okay, so as a room, speed and capacity, get robot position, returns a position object given the robot's position in said room. In the specified room, a random direction and a random position. So we'll say position starting position is equal to a position object where we'll say x is equal to random so we need a random x position which has the width or the amount of columns, right? Random dot random right, random dot random is 0 in between a and b, just enter rand int. Between 0 and the room dot the x has to do with the width, so width, and then the y is equal to a random dot rand int between 0 and room dot height, right? Now I don't think we need to save the room object here, and I'll say self.position is equal to initialize a robot with a given speed and cleaning capacity in the specified room. The robot initially has a random direction and a random position in the room. So direction, does the position have a direction? Do we need to set a direction? Angle, float representing angle in degrees. So this just gives you back a new x and a new y. So get new position gives an angle of any given speed using get x and get y. So what if we make this easier on ourselves then, right? What if we use, instead of this, let's create a position, right, where, let's create a position where x is equal to 0, and we'll say starting equals to a position object where we have our x equals to 0 and our y equals to 0, right? We'll go ahead, we start at 0, 0. But what we'll do is we will go ahead and say no, I don't want to start. I was going to start at 0, 0 and then use that function to get a new position, a random position, but let's not do that. Let's go back to our original format here. This guy. And then now, do we need to give this an angle? It has a direction. I'm not sure. As a rand is zero and 360 degrees. Returns a robot's position. Return self.position. Really? Return a position object, the robot. Okay, easy. Get robot direction returns a float d, giving the direction of the robot as an angle in degrees. Easy. Return self.direction. We're going to float this random. Set robot position. Set the robot self.position. Do we just set it equal to this new position object? Set robot direction. Self.direction. Whoa, make sure. This is assuming this is a position object, right? Update. Simulate the braze passage of a single time step. Do not implement in subclass. Okay. I think that is it for problem 1. What do you guys think? I don't know. It seems like I might be overthinking things and thinking there's like some sort of trick going on, because Well, I mean, I have no other reference, so I have no problem going here and being like, I am solving P-set 3 of MIT 6.0002, and it is a little simple, so I am thinking there is some kind of trick involved. LOL. I am overthinking my answers. They don't want or don't ask for like error checking or type checking. They assume the types of params correct, etc.
Giant Widow says the only thing is that I think the position coordinates should be floats instead of ends.
That's probably right too. Yes, the position coordinates are floats. So we have a position here which has x and y given by floats, x and y. Exactly. Yep, you're right. So then we would say now, is there something we need to change specifically for? Oh, here, right? So random x, so we would say this, we would need to float cast this guy here and then this guy here. Thank you for that reminder. That is a good point, my friend. Who was that? Gian Guido. Hopefully I said that right. I see exactly what you mean. MIT's problem sets often make things look more complicated than they are. Usually the trick is that they assume all inputs are well formed. You don't need to overthink like type checking, bounding, or fancy randomness handling. Looking at your robot imp, a few points out. So if your room width is 10 and random is your return time, which might be outside the room. If you're at 5, you're still in the room, right? You're just hitting the wall. You can't go past the wall. You're in the 5th tile. That's what it means. Like, it's not... The wall isn't 5. The wall is between 5 and 6, right? The 5th and 6th tile, or the 4th, and however big your matrix is. So the wall is in between each tile, so it's like, it's not 5.5, because that's halfway through a tile. I guess it would be at the start of the 6th tile, actually, so the end of the 5th tile. So which might be outside the room if positions are 0 index, so 0 through 9. Oh no, okay. The direction of the degrees is the same as 0 degrees. Oh, that's right. That's a good point. 360 degrees is the same as 0, so 359 would be the better way of saying that. That's a good little trick. That's a good little point. So I'm going to take it back and I'll say, okay, so these are tiles where the well, you have 5 tiles with a length of 4. No, you have a length of 5 with an index cap at 4, right? So like where you can be on the final tile in the matrix, but can't go further. So you can be on the nth tile. If your room is divided into tiles like a grid, then the valid positions from 0 up to the width for x and 0 up to the height inclusive, because you can stand on the last tile, but you shouldn't generate a position outside of the room. Using random nth room width actually works for tiles because random AB includes these endpoints. Your robot can be on the first tile, 0, or on the last tile, which is the width, which is exactly what you want. So because we could have gone one further if that rand int did not include like range, right? Range is exclusive of that final value. You're casting floats, that's fine if they're float values. Perfect. Yeah, oh, here, yeah, see, look, 0 and less than 360. Well, we're actually missing out on a whole degree. We're missing out on a whole degree. So how can we use the random module to exclude the 360? Well, actually, we are missing out on the whole degree. And so let's actually think about it. Hold on, let's think about it.
Giant Widow says you probably want to use random, which generates floats.
So what if we use random and use that as a multiplicative factor against 360? Right, this will give us a float value between 0 and 1, basically a percentage value. Multiply that by 360. No, because I feel like we're still going to miss out on some values. That's not as... We're only going to get 10 values rather than a bunch of different values. 360 and like... You don't want to factor it down by 10 percentage points. No. That's not what we want to do. We want to... don't want a single integer. Because you can have oh, well, actually, no. You don't have floats on direction. A float D. Oh, you do have a float direction. A whole degree. 3. 359.9 and only giving whole. Only gives you whole int, so your robot can only be at 0, 1 through all these. In a set of limitation, your robot would now have a direction like that. So random uniform generates anywhere between that. Ah. I didn't know that. Random uniform. Where is that in the docs? Oh my gosh. Python function in random. Random uniform. Oh, it's like right there at the bottom. It's like 2 scrolls down. Bruh. Return a random float pointing number n such that n is less than or equal to, which is less than or equal to b. Oh. Random uniform. That includes 360, right? So we have 0 and 360. Double chance. Random uniform generates a float in 0 and 360. That does include 0 but excludes 360. No way, dude. That's not what this says, right? Random uniform. This expresses that the B val is inclusive. Oh, so we were close on scaling. That's what they're doing, but they're just doing a percent change. A change, not percent change, but a change with them and then adding it back. Interesting. Taking the difference between the end to the start and then adding the start back to it. But that's multiplied after it's multiplied by the random 1 to 0 factor down. So we were kind of on the right track with the factor. We just needed to factor the difference between the delta between the end and the start and then add back on the start. Okay. So random dot uniform, and we're gonna do 0, 360 here, depending on rounding. Okay, cool. So let's throw in this here. Okay, I have solved problem 1. It's exactly what it wants. Problem 1. Initial random position, you handle the boundaries, random float, random 1 initial direction as float, uniform 360, simple getters instead of position and direction, no extra checks are needed. Subclass of the robot, yeah, that will be problem 2 for the movement strategy. Cool. And then I'm going to throw in my rectangular room one here just to get some feedback on that one before we go. Here was the first part I already finished. So start tile with each dirt amount. Each tile is cleaned. Counts clean tiles, simply works. If you're indexed by 0, no, our tiles are self.width is 5 tiles. So position 5.1 would be out of bounds. If your tiles are indexed by 0, width -1. No, we want to include the width. The width isn't the boundary. The width is the final tile. Ooh, whoops. Oh, I didn't implement this one? I skipped this one? Oh, my bad. Alright, let's do this one really quick. And then I'm gone. Mark the tile under the position as clean by capacity amount of dirt. Assume that position represents a valid position inside this room. Can be negative, which would mean adding dirt to the tile. The amount of dirt to be cleaned in a single... No, the amount of dirt on each tile should not be negative. If the capacity exceeds the amount of dirt on the tile, mark it as 0. So this capacity is kind of throwing me off. Oh, so capacity is how much room it has left. And then if you're full and you start going back over, it would be negative. Okay. So given the position and the capacity, so tile equals to self.room index position.x position.y. We'll say if so the tile has a dirt amount, which is the tile or dirt amount. So if tile dirt amount is less than the capacity, but then we reduce capacity, right? So we'll say capacity less equals by the tiled dirt amount. So if there's less dirt than we have in the available capacity, then we have, if the capacity is greater than that dirt, then we can suck it up, right? And so we'll lower the capacity by the dirt amount, and then we'll set self.room index position dot x index position dot y equal to 0, right? If it's greater than or equal to the capacity. So if the capacity remaining is like 5 and 10. So if it's greater than or equal to capacity, we can take it out, right? So if the capacity is 5 dirt units left and the dirt on there is 2, we can take it. If there's 5 units of capacity and there's 5 units of dirt, then we can take all 5 units and get that out. So else, right, the dirt tile cannot be we're going to, so in all cases, actually, we can lower the dirt tile by the capacity, or the capacity by the dirt tile. But we set the self.room value in this case to equal the delta so the tile then will equal, let's say that the capacity is less than how much of the dirt. So you have 1 capacity for 2 dirt, so it'll just be tile dirt less than the capacity. Are we returning anything? So let's think about this. The tile dirt amount is that value at that matrix position, right? If the tile dirt amount is less than or equal to the capacity value, meaning the capacity value is the amount of dirt that will be cleaned in that step. So if we can clean 5 values of dirt, and we have 5 values of dirt to be cleaned, we will set all 5, we will clean all 5 and set it to 0. Or if the tile is 1 and capacity is 5, we will set it to 0 and reduce capacity down by the tile amount no matter what. Now, in the other case where the dirt tile exceeds the capacity, well, we will take the difference from capacity out of the dirt amount, and that is the remaining dirt left over that stays on the tile. Oh, so capacity is just how much it can clean in each step. We're not keeping track of like a fullness. basically. Oh, okay. Just that's what capacity. It means how much it can clean in each step. Okay, got you. So wants us to floor. What, would we not floor the position? So the y is the amount of rows, and x is the columns. Yeah, so the y is the amount of lists. Ah, yeah, so you have to flip. Oh, int floors. Okay, I didn't know that. So say, we'll say row. We'll say, sorry. So the x is the column. So the x is the column, right? Because the x is the individual values in each array, right? And each array depicts height for rows. So row equals to int position dot y, and we want to go to row column xy, right? Or you could say no, you go to row, not xy, yx, because it's kind of counterintuitive. It's kind of tricky to get to wrap your mind around here, right? Because the list of lists, right? That's what the matrix is, a list of lists. So the overarching list is all of the rows, which is the height, which is the y value. The individual values within the lists of the list, the individual tile values, represent columns in said row. Now your first row, your zero index row, could be headers, right? For a typical matrix table, but yeah. So we would go row column, and then we go row column, row column, like such. It's kind of counterintuitive to flip the x and y for row column, because you have to think about it as a list of lists, where the outer list is your list of all of your rows, which stack up to height, which equals alias to the y index or value or whatever, y point. Whereas the individual values corresponding to columns within the lists of the overarching list are the x values that span across the columns, which has an alias of width. Man, that's tricky. The subtle point that trips up a lot of people the first time. Visually, think of it visually, right? where you have y0, y1, y2, which is an alias for row. So just think of it, row and the y index are alias, right? Outer list equals rows, which equals to height, which equals to y-axis. The inner list equals to columns, which equals to width, which equals to the x-axis. So room yx is the natural way to index a tile xy because each row contains all the x values for that y value. Okay, so is my function good then? Oh, so you could just, oh, so you could either take 0 or this with a clever one-liner. You could use a max one-liner to depict, right? You kind of use the max as your logic, right? Okay, so no matter what, we're going to have a 0 as like a base case. But then if we ever have something greater than 0, we'd prefer that one instead, right? So you can that's a really clever way of actually kind of logically, that's kind of a clever logic trick by using the max function as your if else, because you have a base case of 0, and if you have anything greater than that, you would prefer it because that's how much dirt is remaining on the tile per the capacity difference. So I need to I need to kind of rewire my brain to look out for when you're comparing across, I guess, a base case and a difference off of that value. You could use a max or potentially min function depending upon the desired output. That's a great way to think about it. Using max or min is like essentially encoding a conditional logic in a single function call, which is both concise and expressive. Max 0, tile dirt less than capacity. The remaining dirt can't go below 0, otherwise you subtract capacity. Min, some limit or value, the value can't exceed a certain maximum. It's really about identifying a base case, 0 for dirt, or a ceiling for other limits, and a relative chain, subtracting or adding. Once you see problems in terms of result equals base case or adjusted value with a clamp, you can almost always replace a small if else with a min or max function. Man, this is the programming. This is the juice we got. You guys are here for, right? This is the good. How many of you guys really like knew this or use this in your programming every day? How many of you guys A knew this, but how many of you guys B actually use this in your if else, right? It might be easier just to logically think about it like this, but you can just reduce it to a single one-liner.
Gianquido says max is just an abstraction of your if statement.
Yeah, exactly. It's just a clever way to thinking about the extraction of the logic inside of a max when determining, across, integers, right? It's pretty clever. It's kind of like a light bulb. All right, you guys. Cool. So that was a fun 2-hour stream. Probably shouldn't have taken us 2 hours, but we had a little detour trying to fix the testing PYC. Unfortunately, the problem set 3 incorporates the testing of this actual problem set incorporates an older version of Python, which is not supported anymore by this built-in module. So, and we tried to get to workarounds to fix it, and it just wasn't really working. And it's not really worth the effort to kind of get it to work, as we're just kind of learning, trying to extract out the actual juice of the material here, rather than kind of, and we can kind of do checking ourselves that's what we did earlier. So we completed problem 1 of problem set 3 here. So this is MIT 6.0002, which is the Introduction to Computational Thinking and Data Science course. It's kind of a prelude into kind of more advanced Python and getting into machine learning. Honestly, the Python isn't really that advanced in my opinion from what they've been showing. The Python that they're having you do in these problem sets is a lot easier than the Python they're honestly showing you in the lectures, um, but which is kind of interesting. But I'm not complaining. I definitely am not complaining. Um, but yeah, I thought that maybe MIT would be a little bit more difficult. It's kind of the difficult part is kind of just understanding what the problem is asking. But the class implementations I just kind of overthink them because they are so simple. But anywho, we successfully implemented two classes: a a rectangular room object which has a 2D matrix and associated variables associated with it, and then and some methods, and then a robot object which has a speed, capacity, and initial random position with a direction, and then obviously some methods. So we're going to implement the next few methods, which are going to be in the subclasses of these room and robots. And so that'll be in the part 2 for the problem set 3. And then we will continue on with the lecture watch along series, which I am doing breakdowns and re-uploading to the channel as well, so you guys can re-reference that and watch it in 2x speed, or just rather than having to find it on all my live streams, I'm just kind of having it there in its own playlist in the channel as like it's a standalone video, and cut out all the chat reads and all the pauses just to get like kind of like the reactions and the note taking solely. Um, so make sure to check that out, and we'll be moving on to lecture 9 shortly after we finish this problem set. But this was so much fun. I really, really appreciate you guys being here. My name is Michael. I'm 26 years old. I got a degree in human biology and a minor in chemistry, and I work as a formulation chemist for a biotech company where I make biological controls in large-scale batch formulation. And I've been teaching myself how to code a little over a year now, every single day about after my 9 to 5 job. So we are very, very dedicated into learning through various resources like MIT 60002, CS50, and various books like Introduction to Algorithms that we are reading right now, Data Structures and Algorithms in Python, Fluent Python, and many more. Shout out, tomorrow I will be dropping chapter 1 read aloud video. I chopped it up and made it like pretty much like an audio book to where it's just fluent reading the entire time, no errors, no nothing, for all of chapter 1 of Introduction to Algorithms. So that book is a heavily used book in many collegiate level courses, both undergrad and graduate. So if you honestly, if you are in undergraduate CS course, you're probably most likely referencing that book in a lot of your syllabus. So for your algorithms courses in your undergrad. So I highly suggest you follow along with that series and watch those videos. So thank you guys so much for being here, and I'll see you guys tomorrow. Bye, guys. So thank you guys so much for being here. Join my Discord. Link down below. I have a Discord which is my entire roadmap of my learning journey so far, where you can get access to all of my resources from every book I've read, course I've taken, notes, and even some stock plays. Your boy, shout out your boy. I was so right. I've been hitting like money. I called Macy's stock. I called it, dude. I knew this thing was gonna heat and heat up, and it did. It did, boy. Let me tell you. Oh boy, yep. We're up 15% here in just a couple of days. I called this one back out in my Discord. I'm not one of those stock guru shills that charges for. I have a pretty good track record, and I'm a pretty adamant retail investor. And I shouted this one out about a week or two, about 2 weeks ago, and I felt that this one was going to hit, and this one did hit. So shout out to anyone that played Macy's with me. We made some no. Anyways, I'll see you.